You run Traceroute inside Azure and suddenly you see stars. Did the packet disappear? Did the network fail? Not exactly. Today we're going behind the scenes to understand why networks sometimes choose to stay invisible. Traceroute does not magically discover paths. It manipulates a field called time to live, or TTL. Every layer 3 device decrements the TTL by 1. When the TTL reaches 0, the router discards the packet and sends back an ICMP Type 11 message, time exceeded. Here's the first deep dive insight. Traceroute depends on the control plane, the CPU-generated ICMP replies. But actual traffic forwarding happens in the data plane, specialized forwarding hardware optimized for speed. So, traffic can flow perfectly even when Traceroute appears broken. When a router chooses to generate an ICMP time exceeded response, that hop becomes visible in Traceroute. But here's the important part. A forwarding device may continue forwarding traffic normally, while refusing to send ICMP responses back. So the traffic succeeds, but Traceroute sees stars. In Azure, networking is heavily abstracted through software-defined networking. When traffic leaves a virtual machine, it may traverse multiple programmable forwarding layers, including the Virtual Filtering Platform, or VFP. These layers can forward traffic transparently without exposing themselves as visible traceroute hops. When two virtual machines communicate inside the same VNET, the forwarding path may remain almost entirely inside Azure S fabric. You may see very few hops, sometimes almost none at all. Azure abstracts the physical topology behind logical forwarding. With VNet peering, traffic may traverse Microsoft's backbone directly without using the public internet. In same region peering, visibility remains extremely limited. In global peering, traffic may cross entire backbone regions while still hiding most transit infrastructure. Inside hyperscale backbones, traffic may traverse technologies like MPLS, VXLAN overlays, or segment routing. These transport systems intentionally hide transit complexity, making thousands of miles of forwarding appear as a single logical hop. When traffic leaves Azure and enters public internet routing domains, visibility often increases. Public ISPs and internet routers are more likely to generate ICMP replies. That's why internet traceroutes often show many visible hops. Now let's place a firewall or network virtual appliance in the path. The firewall may forward your traffic perfectly, while suppressing traceroute responses entirely. This creates one of the most common troubleshooting misunderstandings. Traffic works, but traceroute looks broken. Routers also protect themselves using control plane policing. CoPP generating ICMP replies consume CPU resources. Under heavy load, devices prioritize forwarding traffic over answering traceroute requests. Some devices also rate limit ICMP generation, causing intermittent traceroute timeouts even while traffic remains healthy. Traceroute can be misleading when return traffic follows a different path. Your original packet may succeed, but the ICMP response may return through a blocked or filtered route. The traffic worked, the reply didn't. Here's the deep dive truth. Traceroute does not reveal the exact physical path. It only reveals devices willing to send TTL expired responses. Traceroute shows control plane visibility, not necessarily the full data plane reality. If you see stars followed by successful hops later, the network is usually healthy. These are just silent routers in a hidden transit path. But if the timeouts begin and never recover, you may have a real outage. One packet traversed software-defined forwarding layers, crossed hidden backbone infrastructure, survived control plane filtering, and revealed only the devices willing to answer. That is what really happens during Traceroute. To master cloud networking, you have to look beyond the stars. Subscribe to What Really Happens for more deep architectural dives.